Welcome back, everybody. I'm back, full of coffee, full of energy. So the model, there's two differences with object storage. Difference number one is in object storage, you have this flat key value model where you have objects plus bucket IDs that give you an object. But in a distributed file system or in any file system, you have a hierarchy of directories and files. So it's a tree. So of course, the trees of computer scientists are very different from the trees we see outside. But basically, lorem ipsum is the root, and then it goes all the way down with this hierarchy. And the files that are the leaves of the tree, marked in with the red squares, are the leaves of the tree at the very bottom. So this is the file hierarchy, exactly as you have on your laptops when you organize them. That's difference number one. Difference number two is that in S3, you just have your object and that's it. It's a big black box. You just upload it, retrieve it, but you cannot. There's no notion of any subparts of it. But in the distributed file system, it's different. You cut your file into blocks. So your file can be absolutely gigantic. You can have a petabyte file, absolutely gigantic, but you cut it into these much smaller blocks, which we see it's 128 megabytes. And the idea is that these blocks are going to be read and written one block at a time. And so I said earlier, there is no random access. No random access, let me give the analogy that I used. When you take a book and read it from the beginning to the end, then you're basically scanning the book. You're reading the entire book in sequence, linearly. That's how a book is supposed to be read. Random access, it's like the way you have a recipe book, right? I don't know, has anybody ever read a recipe book like from the beginning to the end? No, right? Because you use it in random access. A recipe book, you just look at the parts you're interested in, the recipe you're interested in. HDFS is the same. We want to read it like a Dan Brown novel and not like a recipe book. So the blocks are supposed to be read in their entirety from the beginning to the end and not in a random access fashion, just a few bits here and there. You could, but it's going to take absolutely forever, and it was absolutely not designed for that. So block storage, so in that case, we have a file, an object, we call them files, by the way, don't call them objects, we call them files in HDFS. So a file has 8 blocks in that case. And the 8th block is less than 128 megabytes. Of course, most of them are not going to be exactly a multiple of 128 megabytes. All right, and so this is called what we call block storage. So you see a file hierarchy and block storage. Be careful, we call that a block. Google didn't call it a block, they called it a chunk. And in fact, throughout the lecture, I'm going to be using plenty of words that mean the same thing because every technology has a different name. So block, chunk, split, shard, partition, and so on and so on and so on, that pretty much all means the same thing. But when you communicate with people, you should still use the word that fits with the technology you're discussing. So if you talk about HDFS, then you should call them blocks. If you talk with Google engineers about GFS, you should call them chunks. In MapReduce, we'll see that we call that a split. Shard is the word that I used earlier when I showed you the data set in S3 with XAA, XAB, XAC, these were shards. Partition would be what mathematicians call that. You basically partition the files into the blocks. So that's the mathematical name, partition, and so on and so on. Don't be scared. They're all synonyms, right? But try to learn which word is used in what context just to make it a bit easier to communicate. And so the summary, so if I take this plus this, I get this. This is the model of HDFS. It's that simple. So we have a hierarchy of directories and files, right? So the directories are in blue. And then at the leaves, we have the files, 3 of them, and every file is associated with a sequence of blocks. So here we have 8 blocks for that file, 3 blocks for that one, and 4 blocks for this one. Who is with me? Who finds this simple? That's a simple model, right? The hierarchy of directories and files, every file is a sequence of blocks, period. That's the model, right? That's simple. Okay, so why do we have all of these blocks? We are going to put these blocks, of course, all over the cluster. right? So what's really nice about having blocks like this is that we can nicely put them all over the place. For example, on the left, you have a monolithic view. That's as if you have just your laptop right here. That's how it would look like. You just have one drive, and the drive has all these blocks. So on your laptop, it's 4 kilobytes, the size of a block, but it's monolithic. There's just one machine, one drive for most people. But on the right, we realize that all these blocks are actually distributed on the cluster. So imagine now I have 8 machines on my cluster. It's actually more than that. Then I have a few blocks here, a few blocks here, a few blocks here, a few blocks here. And everything is done in such a way that you basically spread the blocks all over the place. Typically, you're going to have a few thousand blocks on a machine, right? So a few thousand blocks here, 1,000 blocks here, 1,000 blocks here. And it's really spread out all over the cluster. You just spread them all over the machines, just like you would spread Nutella on a piece of bread, right? You just spread the blocks all over the cluster. And now the size of the block, that's the question that I ask you. So on the left, this is your laptop. What you have on your laptop, it's read in 4 kilobyte blocks, very typically. And in HDFS, we have the order of magnitude is around 100 megabytes, so 128 megabytes for HDFS. 64 megabytes was what Google was using, I think 64, and also what some distributions of HDFS were using. Yeah, HDFS is like Linux. You have Debian, you have Ubuntu, you have distributions, and HDFS also has distributions. And some of the distributions of HDFS have a default of 64 megabytes. The standard one is 128 megabytes if you download it directly from the project page. It's configurable. If you're not happy with that, you can change it. In fact, it's cool to experiment with, because what you can do, just to play with, is change the size of a block and make it 4 kilobytes, just to see. And then you see how it suddenly starts to be unusable, right? You can just try and experiment, or maybe try to put it a much larger size, like terabytes or even, and then you will see again, it becomes unusable. Then you notice there is a sweet spot. There is really a sweet spot at 128 megabytes. It's large enough that you're going to have a lot of data flowing, because 100 megabytes, that's a lot of data, takes a while to download. At the same time, they are sufficiently small that you can spread them all over the cluster, right? So it's really a compromise between the two. Okay, so that's the intuition. So that was the model. A hierarchy of directories and files, and the files are sequences of blocks, the size of which is around 128 megabytes. This number is going to evolve with time, right? Because the hardware changes, so this is drifting. I think Microsoft is slowly shifting to gigabytes for blocks right now. They announced, I think, at some point a higher block size. This is just because it has a life, right? Things are evolving, but still the order of magnitude is more or less the same. So that was the model, and now I'm going to tell you the secrets of how HDFS is actually implemented and what's actually going on behind the scenes. So let's look at the architecture. So I told you, HDFS is installed of tens of thousands of machines, many machines. Obviously, these machines need to communicate. And whenever machines need to communicate, you need to connect them, and you need to have some organized way of them to communicate, right? So 2 machines, it's obvious. But for example, if you have many machines, one way is to connect them all, right? That is known as a peer-to-peer network. That was maybe 25 years ago, peer-to-peer networks were very, very popular over the internet. People could just download a lot of things from the internet very easily. Yeah, that's one way of doing that. But we're not doing it that way with HDFS. No, we are doing it in this way. Centralized, so we have one machine in the data center there's many ways to call it: coordinator, primary, main leader, and so on and so on. And then we have the the machines that will store the data, as we will see, worker, secondary, follower, and so on. Many, many different ways of calling them. So again, not a peer-to-peer network like that. We are not doing it in this way. We have a centralized network topology with one coordinator and plenty of workers. So concretely, this topology, in the case of that's the general name of the topology, we'll see it many times in this course, also with the other technologies. But in the case of HDFS, we have a name for the coordinator node. We call it a name node. And we have names for the worker nodes. We call them data nodes. You'll see it in a single word. You might also see it camel case with the uppercase N also for node, like in the Java classes. But it doesn't really matter, right? Name node, data node. And of course, the data nodes are called data nodes because this is where the data is. This is where the blocks are. And the name node is called in that way because this is the one that keeps track, if I simplify, the names of the files and directories. So name node and data nodes. All right? Now, obviously, a data node doesn't just have 3 blocks, right? I oversimplified on the slides. In reality, it has a few thousands of blocks on each data node, right? Okay, so now let's take the perspective of one file, just one file. Let's say a large file that is a few terabytes. So if I take that file, on the logical level, a file is just a big sequence of zeros and ones. So I divide it into these chunks that we call blocks in the context of HDFS. Let me take 128 megabytes for the size of a block. So now I have 1, 2, 3, 7, 5. How am I counting? 1, 2, 3, 4, 5, 6, 7. So probably slightly bit less than a gigabyte in total. The file that I'm looking at. And then I'm going to do one more thing that I haven't told you about yet. Is that I'm going to replicate multiple times these blocks, multiple times. The default is 3. 3 is a pretty good number, right? If one fails or gets corrupt, you still have a majority vote on the other 2 that look alike, right? So that's also how if you want to create a company and you do it with 3, if there's an argument between 2 people, then the third one can help, right? So this is why we like the number 3. So every one of the blocks will be stored 3 times on 3 different data nodes. So I put the orange one as an example 3 times. It can be more, it can be less. You can change actually that behavior. I might have overdone the green and the blue one because I put 4 greens and plenty of blues. But anyway, the default is 3 replications. All right, and so that means you have to keep in mind, whenever you want to store a logical file of a gigabyte, it's actually going to eat 3 gigabytes on the actual storage because of the replication, right? And so replication is one of the secrets for fault tolerance. If a drive crashes, let's say, for example, this machine goes down, crashes, it's lost, that's okay because you have another copy here and here of the block. All right. So now the central point of access is the name node. Whenever somebody wants to connect to the system and fetch some files or write something, the first point of contact is the name node. And maybe now you understand why it's not a worldwide service, but it's at the scale of a company, because in a company, it's fine. You have a machine, everybody connects to it, that's fine. Imagine a worldwide service where the whole world connects to a computer in the garage of the founder of Amazon. That doesn't make sense. You would crash the computer. But at the size of a company, that's fine, right? So here we have just that machine that handles all of the requests. Okay. Now I'm going to zoom in on the name nodes, and let's look what's inside the name nodes. So if I zoom in, this is what I get. I'm going to go through these 3 things in there. The first thing there is in the name node is the file namespace. What do I mean with that? It's the tree, it's the hierarchy of directories and files. What I really mean here is the hierarchy with the names of the directories and files, not the actual data, because the data is there, as we know. But it has all the hierarchy with the directory names, the file names, plus some access control. You might know that's the case on your laptop too, that when you create a file, it has a user that owns the file. It might have a group, and it might have read access, write access, and execute access, and so on, right? Who knows that on your laptop? If you list the contents of a directory, you see that. That's called access control. And so it also has that. It also can manage some user knowledge about the users and who has the right to read and write every file. So all the names, the entire hierarchy, the access control lists, and so on, that's all in there. It's in the memory, in the working memory, the RAM. Number one. Number two is that every file, so these are the leaves of the tree, so these are directories here, and directories, and here these are files. At the leaves of the tree, these are files. Every file which has a path, right, that's the path in the tree, is associated with a sequence of block IDs, not the actual blocks, because again, I repeat myself, the blocks, they are on the data nodes, right? The block IDs. So I have here this file that has the green block and the blue block, right? Just knows the identifiers of the blocks. File 2 has the black, purple, orange, and red block, and file 3 is just made of the yellow block, right? In reality, it's not colors. It's going to be more like numbers, but this is the idea. So you map each file, each leaf of that tree, each file, to a sequence of block identifiers. Number 2. And number 3 is basically a mapping from all the block identifiers to the location of the actual blocks. So for example, the green block, the name node knows that there is a copy of the green block right here, and there is another copy of the green block right there, right? Normally, in a properly working system, there's going to be by default, three copies. By the way, the copies are called replicas. This is one replica of the green block. This is one replica of the green block. There is no such thing as a first replica, second replica, third replica. There's just 3 replicas, no particular order, primus inter pares, like the Bundesrat, right? So just these 2 replicas. All right. The hierarchy, the mapping of the files to the block identifiers, and the mapping of the block identifiers to the location, meaning the data nodes on which there is a copy of the blocks. Who is with me? Right. So these are the 3 things on the name node. And the name node is responsible, so that's the central point of contact, for when a user wants to create a directory, delete a directory, in which case the name node is just going to be modifying this, right? When you add directories, it's just adding them to the tree right here. Write a file, of course, that it will not do alone. It will orchestrate the whole thing with the data nodes. Append to a file, read file, delete a file. So that's the first point of contact for doing any of these is always the name nodes, right? And I will have a few animations for you after that. All right, so now that's the name node, that's this. Now let's zoom on the data nodes now. You see, it's actually going to be pretty simple because on the data node, there's data. So there's the blocks. So imagine if I zoom on one data node, typically there will be a few thousand blocks in there. Each 128 megabytes or less, right? The last block of a file might be less, right? All the blocks except the last one are exactly 128 megabytes. The last one might be less. So thousands of them. Now, where are these blocks stored? Well, they have to be stored somewhere. And actually, they are going to be stored on disks, on the disks that are within the machine we're looking at, right? In fact, if you could, and you can even do it as an exercise, if you would actually connect to one of the data nodes with SSH, SSH is a protocol to log in remotely to a machine, and you would look at the disk of the machine and read from the disk, you will see that every HDFS block is an actual physical file on the hard drive. Right? You will see them as actual files on the hard drive. But that's a physical implementation of the block, the way that it's stored on the hard drive. Okay? And data node basically has the drives, monitors the drives, it checks if they're still working. So there's a lot of monitoring in place so that a node is capable of detecting that a hard drive is no longer working. It's capable of detecting that some of the data might be corrupt, right? Also, we have a way of detecting that an entire node has crashed. An entire machine has just completely left the cluster. All right. By the way, the block IDs, I told you it's not colors. I use colors because it's nice on the slides, but in fact, it's an integer. 64 bits basically means it's an integer between 0 and 16 quintillions, I think, if I'm correct, between 0 and 16 quintillions. So you have a lot of space for storing blocks, right? 64 bits is much more than we need. All right, and one block ID uniquely identifies one block. So the block IDs, this is what I told you are here. Each one of them would be basically a 64-bit integer, right? And these two are block IDs right here. And here, these are the actual blocks on the data nodes. Okay, that's the block ID. Who is with me? Okay. So now I'm going to tell you how all of these communicate with each other. The name node with the data nodes, the client, so meaning the user with the name node, and then the user with the data nodes, right? So there are three places that I need to explain. First, I'll explain this one. Then I will explain this one. And then I will explain this one. I think it's that order. Yes, that's the same thing, just with more details. So basically, the name of that protocol here between the client and the name node is called the client protocol. The name of the communication between name nodes and data nodes is called the data node protocol, very original name. And then the name of the protocol to communicate between the clients and data nodes is called the data transfer protocol, because this is where the actual data is actually flowing, right? So this is where the data is flowing. Okay, so let me start. As I said, I'm starting here with the client protocol. So this is a machine that wants to create a directory, delete a directory, write a file, read a file, so whatever it wants to do, and it connects to the name node with the intent of doing that. So this is what we call metadata operations, creating a directory, deleting a directory, and so on. And so the client connects to the name node, and the name node is going to reply. So for creating a directory, it's just going to confirm, yes, I created the directory. But if the client wants to write a file or read a file, then the name node is going to reply, yes, I understand you want to read or write a file. These are the locations of the data nodes that you're going to have to communicate with. So if you want to read a file, these are the ones that you need to ask the blocks. And these are the block IDs that you need to request. Where do these block IDs come from? They come from here, right? This is where the name node gets the block IDs after the client. Let's say the client requests dear file1, read access, and the name node will reply with these two block IDs, plus the locations where these two blocks are located, right? So this is what you get as an answer from the name node to the client. Then we have the second protocol, which is the data node protocol. So the data node protocol is right here. Name node, data node. So the data node protocol has several components. The first component is the registration. The cluster of machines over a very, very long period is going to have new nodes and nodes that leave, either because there's a crash or because the node is taken down because it wants to be, we are replacing it with a more modern machine or something. So when a data node joins the cluster, it registers itself with the name node, like, hello, I'm here, and I'm joining the cluster, and now I'm available to store blocks, right? So this is the registration. From the moment a data node has joined the cluster of machines, every 3 seconds, by default, can be changed, every 3 seconds, the data node is going to send what we call a heartbeat to the name node. It's like, I'm here. I'm still here. I'm still here. And like this forever, well, until it crashes or is removed from the cluster. Every 3 seconds, we have a heartbeat. What we also have, but of course not every 3 seconds because that would be too much, more like every 6 hours, we have a block report. So the block report is a full list of all the block IDs that have data, that have their block stored on that data node, plus maybe some hashes and checksums just to check for corruption, right? So that the name node can check that everything is all right. And then the fourth thing is block received. So this is after the client has just written a new block. I will show you the animation later. If a new block was written to a data node, the data node confirms that it has received the block. It sends a message to the name node saying, hey, I've just received this new block. And that's it. So these are the things that happen. In the other direction, the name node can send instructions to data nodes. For example, it could tell to the data node, hey, this block here doesn't have enough replicas. It's only stored twice, maybe because one of them crashed. I'm giving you the instruction to go to that data node and fetch a copy of that block and keep it. And now we are back to 3. So this is called the block operation, and this is to basically manage the whole cluster. However, the name node is never, ever going to connect to a data node. Now you're going to tell me, what is this? How can it never connect to a data node and give instructions? That's because it's giving its instructions as an answer to the heartbeats. So if the name node wants to request something from the data node, it has to wait for the 3 seconds until it receives the heartbeat, and then as an answer to the heartbeat, say, hey, by the way, please do that. Okay? So it's always the data node that connects to the name node every 3 seconds. Who is with me? Right? Okay, very good. Okay, so we've taken care of the first 2, client name node, data node, and now with the client and the data node. Now this is where the actual fun happens because this is the actual data, the actual blocks. When a client writes a new file, it's going to write the blocks. What's going to happen is that there's a pipeline that is created, and the 3 data nodes that have been designated to receive a copy or a replica of the block are going to be nicely arranged in a queue, like this in a line. And the client is going to ship the block. This is going to be shipped again and shipped again, right? So that it's 3 times. So this is a pipeline. So it's not like the client communicates with the 3. It only communicates with the first one, and then it's shipped in a pipeline over the network. Who is with me? Right? So this is for writing. For reading, the client only needs to connect to 1. Right? When you read, you only need to connect to 1 data node. That's all. Okay. 1, 2, 3. So that's now we have the whole communication pipeline in there. So now you know how they talk with each other. And because you know, yes, we have a question over here. There you go.
The connection from the client to the data node, is that always assuming that we have multiple clients or may have multiple clients, is that always the same node to the data node? Is that always the same connection to the same data node, or may there be, for different clients, be connections to different data nodes? Or is it like we have one data node that takes the role as, let's say, the front data node?
So you say data node, but do you really mean name node?
I mean,
in that case? Oh, this one?
No, yes.
Yeah. Mm-hmm. So the data node is going to be different every time. So for every block is going to be a different data node. And how do we know which one it is? From here. So the name node here will always give to the clients the location, so the data nodes that it's supposed to communicate with. And based on this, the client is then communicating with the data nodes, right? So in summary, there is only one name node always the same one, but the data node is going to be a different one for every block that we read or write. Thank you. Any other questions? Yeah.
If you go back to the previous slide, it's not, I don't know which, this one. So the data itself goes through the name node, going to go back to the client. So once you've made a request for a file or parts of a file, the data blocks that you need, they go through the name node or they go from one of the data nodes to the client?
Directly from the data node to the client.
Directly from the
The name node never ever sees a block.
Okay.
Never.
Okay, okay.
Yeah. Awesome. Any other questions? You can ask all the questions you want, right? Okay, very good. So now, oh yes, there is another question. Go ahead.
When data is being written to the data nodes, how did the blocks get created? Because I guess you have a large file, and how do they get split into blocks? Where do they
Yes, exactly.
Split?
Yeah, this is when they get created. The client is basically shipping the blocks, and every time there is a block, it's creating a pipeline and then shipping it.
So the client makes the blocks?
Yes, yeah, okay. Absolutely. In conjunction with the name node. So the name node instructs the clients on where to put them, but yes, the client is creating the blocks. Yeah. Okay. Any more questions? On Zoom, nobody's asking questions on Zoom. You can ask questions on Zoom, right? You can just write in the chat, and then Zika will read them out loud. Yes?
I'm not sure I fully understand the difference between the cloud blob storage and this, because essentially, if I cut my blobs small enough, they could become blocks. And then I'm essentially, so what's the difference in functionality?
I'll come also to the Zoom question right after that. Yeah. There's two differences. The first difference between cloud storage and HDFS is that cloud storage is a worldwide service, right? You don't need to take care of any installation or anything. You just create an account and there you have it, right? It's centrally managed and you can rely on it. HDFS is not a cloud service. If you want an HDFS cluster, you have to create it. Either if you have a large enough company, you have enough DevOps and engineers that's going to take care of ordering the machines and installing it. But in fact, you can also create your HDFS clusters with just a few clicks on Amazon or Azure. You can just click. In 5 minutes, you get an HDFS cluster. But it's your own cluster. Nobody else is using it, right? It's creating just for you. So that's the first difference. Now, the second difference, let me start with S3, then I come to Azure. In S3, there is no such thing as blocks that objects are made of. An object is an object, and that's it, right? Up to 5 terabytes. However, and here I'm getting a bit more into the details, when you upload an object, you have the possibility to upload it in multiple parts. But these are not blocks. It's more like a protocol for uploading that you say, okay, here's part 1, here's part 2, here's part 3. Now glue them together and you have an object. But then it's forgotten. The object is created. So there are no blocks in S3. And probably this is the reason why there's this 5 terabyte limit. Now, Azure Blob Storage is kind of in between. It's in between S3 and HDFS. So this is the reason also why the Azure Blob Storage has much larger sizes of objects that it can store. And there is even, I think they call it Azure Data Lake on top of Azure Blob Storage that introduces this whole hierarchy of files as well. So you can view somehow, and this is the evolution of things, as the Azure Blob Storage or the Azure Data Lake as an enhanced cloud service that kind of offers some features that HDFS would otherwise have. You can see it in this way. Yeah, right? Yes, any other questions?
We got a few questions on Zoom.
Zoom. I was about to forget. Yes?
Yes. First, Olaf asked, do we always communicate with the main data or also the backup of the same files?
So the first thing that I would say is there is no such thing as the original data and backups of the data. So every block is stored 3 times, but these 3 times are symmetric. None one of them is more original than the other 2, right? It's just 3 copies. And concretely, that means that when you read a file, you could connect to any one of the 3 copies. In practice, you are going to connect to the copy that's nearest to you. So it basically depends where you are, and you connect to the nearest one. Does that answer the question? Yep, awesome. And then the second one?
Yes. Manuel asked, are the data nodes the actual physical location of data, or are they still part of the model?
So let me get more into details. In the way that I drew things, basically, a name node is a machine and a data node is a machine. So we have one machine that acts as the name node, and we have thousands of machines that are data nodes. If I get more precise, the name node is not a machine, it's a process that runs on a machine, a piece of software that runs on a machine. Likewise, the data node is a process that runs on a machine. So you have 1,000 machines, and each one of these 1,000 machines are running a data node process. Just like on your laptop, you might have a browser open, you might have, I don't know, your mail client open. These are processes running on your machine. And the name node is a process like that as well, and the data node is a process like that as well. And I'm saying that because we'll see in the coming weeks that there's going to be other processes that are running on the same machines, right? So the name node and the data node are really just the names of the processes that run and make HDFS work, right? So they're part of the physical implementation, right? Does that answer your question? Yep. All right.
Yes, and also Simon asked, between HDFS S3 and laptop, what are the considerations when choosing the format of the drives, such as different file system like NTFS, and which specific ones are usually used for HDFS and S3?
I think the way the hard drive is formatted is an implementation detail. You could pretty much use any, and because that's a physical implementation, right? So you could have an HDFS on pretty much any hard drive format, right? You know what it means, the way to format a hard drive. The way Windows does it is different than the way macOS does it, which is different than the way Linux does it. So it's just the way you organize the bits on the hard drive. But this plays no role for HDFS. It's because when I say the blocks are stored as files on the hard drive, they are stored in whichever way the hard drive is formatted, right? When you get the block, it's just a bunch of zeros and ones in the end. So the way it's formatted on the physical disk is completely orthogonal to that. Does it answer your question? Yep. Any other
And
pending
also, Simon also asked, how does HDFS replication of data compare to the RAID, RAID?
I didn't get the last part.
RAID, RAID.
Oh, RAID. Oh, yes.
Yes.
Let me say a few words. It's nice because this question comes every year. Let me first explain what RAID is. So it means, correct me if I'm wrong, redundant array of inexpensive disks, right? Not everybody has a RAID mount at home, but maybe some people who love computers do. So the idea of RAID is that some people at home have bought, let's say, 4 hard drives, 4 of them. And they just pile them up in some kind of tower. And then what happens is that these 4 hard drives together act as a single hard drive. But the way that it's done is that there is some replication across these hard drives that make it safer, right? It makes sure that if one of our hard drives crashes, then the other 3 hard drives have the data, right? So it's it's already quite, it's been there for quite a while. So it solves the problem of fault tolerance locally in your home. Now, the idea of replicating across drives in RAID is very similar to the idea of replicating blocks in HDFS. It's just that HDFS is way bigger than RAID. But another very important aspect to consider, and a question that is often asked is, does it make sense to implement HDFS on a cluster of machines such that on every machine there is a RAID mounted, multiple disks mounted as RAID? And the answer is, it's totally useless. It doesn't make any sense because we are already replicating the blocks across multiple machines. So if on top of that we add RAID, it's just not bringing us anything, right? We already have the replication in HDFS. Does it answer your question? Yep, awesome. Very good. Any other questions?
Yes, Manuel has a follow-up. So the data nodes are not the final position in memory where data are stored. They are physical processes that we use to model, but still not the final position of the data. Is it the case?
Let me see. That was a long one. Yes, I think the answer is yes. So a data node is just a piece of software that is running. Again, just like you look on your laptop, you might have a browser and a mail client and maybe Word or Excel or whatever. These are processes, right? Excel, if you use Excel, is not the place where your data is stored. It's just a piece of software that reads it. But when you have an Excel file, the file is actually stored on the drive, right? So here is the same thing. The data node is the process. It handles the communication and the monitoring and all these things. But the actual data, the actual block, is a physical file on the local hard drive of the data node. Right? So from the perspective of HDFS, it's a block. From the perspective of the tiny local machine that is handling the block, it's a small file on the disk, a 128 megabyte file.
And I also want to add that usually in the data center, the operator can co-locate, like, for example, the data node process with other application on the same server. So that, yes.
Absolutely. And we'll see that exactly in a couple of weeks. Absolutely. We'll have other processes that run on these same machines. Yeah. Does it answer your question? So there's some physical memory dedicated to each data node. Yes, a disk. So imagine 10,000 of machines. Each one of these 10,000 of machines runs a data node process, and each one of these 10,000 of machines has one or more local hard drives connected to them. And these local hard drives that are connected to every machine are the persistent memory where it's stored. It's not the working memory, right? Not the RAM that you lose when you shut down the machine, the disk, the physical drive, the hard drive, right? Yeah, all right. But it's very nice to ask this detailed question because that makes it clear, right? So even though HDFS is at the size of a data center, in the end, the data has to end up on some hardware, and the hardware are the disks. It's like physicists say, information is physical, right? The zeros and ones, they have to end up somewhere in our world, right? And here they end up on disk, on physical disks. Any other questions? No other questions? It's nice that we took time to have questions. So what I'm going to do is I'm going to stop here because I see it's already 10. What comes next, and that I will do next week, is actually an animation that starts here. I'm not going to start today, but basically I will show you when we read data or when we write data, I'll animate it. I'll show you exactly what is going to work, right? So this is what I'll start with next week. Then I'll tell you about the replication strategy and some tricks to make the system more available and more resilient. But you pretty much know now the model. Hierarchies of directories and files. Files are divided in blocks, and the architecture, one data node, one name node, and plenty of data nodes that store the actual blocks, 3 times each. Thank you very much, everybody. I hope you enjoyed the lecture and enjoyed the exercise session this week, and I'll see you next week where we'll finish that lecture and then we'll look into syntax, a bit of XML and JSON. Goodbye. Thank you.